Imagine you're guarding a border and your radar spots a massive jet heading right for you. But when you look out, there's absolutely nothing there. Or worse, your screen tells you there are 50 jets, all flying in different directions. How do you track something that is actively trying to lie to you? Well, that brings us to our first hurdle, the modern radar problem. Before diving into quantum physics, we really need to understand why our traditional radar is suddenly failing us. For decades, radar was the absolute king of the skies. But today, the sky is full of things built specifically to confuse it. Take a look at this. It's a miniature air-launched decoy, or MALD. It's a sleek, 280-pound cruise missile. It's tiny, but to a radar system, it perfectly mimics a massive bomber. Why? Because it literally broadcasts fake screaming signals. A swarm of these can completely flood a defense screen with ghosts. See, traditional radar is basically a giant floodlight. You shine it into the dark and hope you catch a reflection. But a floodlight has two massive weaknesses. First, stealth targets are painted in materials that absorb that light entirely. They're practically invisible. Second, decoy targets just shine a million infinitely brighter flashlights right back in your eyes, blinding you. It's a literal game of cat and mouse. And honestly, the floodlight is starting to lose. So how do we fix this? Enter the quantum radar. To beat these modern deceptions, physicists are tossing out classical radio waves and stepping into the weird world of quantum electrodynamics. We're no longer using massive sweeping waves. We're using individual countable particles of light. Think of it this way. If classical radar is a glaring floodlight that anyone can see and spoof, quantum radar is an unbreakable secret handshake. It uses a tiny, completely undetectable number of particles. It's so quiet, the enemy target has no idea it's even being watched. There's no loud radio wave to trigger their alarms. It's perfectly silent and perfectly secure. Okay, but how exactly does quantum tracking work? How do we actually pull off this secret handshake? Well, we use quantum entanglement. You've probably heard Einstein call this spooky action at a distance. It basically means two particles are intimately linked, so whatever happens to one instantly relates to the other, no matter how far apart they are. Here's the trick. The radar system generates a pair of entangled twins. We keep one safely at home, we'll call that the signal twin, then we fire the other twin, the idler photon, out of a telescope and into the sky. When it bounces off a target and comes back, we compare its precise arrival time against the twin we kept. By comparing these two timelines, we can find exactly where the signal spikes line up perfectly. This is a process called cross-correlation. Imagine the top pattern is the timeline of the twins we capped, and the bottom is the timeline of the twins returning from the sky. When those top and bottom spikes click together perfectly, boom, we have a confirmed, undeniable hit. We know exactly how far away the target is. But here is the massive catch. What if the target is moving at hypersonic speeds, like Mach 8? Time literally moves differently for incredibly fast objects. We actually have to correct for special relativity using a math equation called the Lorentz factor. If we don't apply this correction for time dilation, our twins' timing windows will be completely misaligned and the target will slip right past us like a ghost. But when we do factor in that relativistic time shift and the Doppler effect, we get this. Look at that. Perfect 3D spike rising right out of the noise floor. That is our target. It doesn't just tell us where it is, it tells us exactly how fast it's moving, with insane precision right down to the millimeter. Now for the really cool part, beating the jammers and decoys. How does this incredibly complex math actually stop a swarm of decoys? Because remember, those missiles are out there screaming fake radar signatures to overwhelm us. Here's the genius of it. The quantum radar relies entirely on that unbreakable, entangled link between our specific twin photons. So if an enemy jammer blasts a billion fake photons at our receiver, the system just shrugs. It checks them against our signal twin. No entanglement, no match. All those fake signals are instantly thrown in the trash as background noise. The target's disguise is completely stripped away. And here is exactly how we expose the physical decoys. When photons bounce off a massive, real bomber, they hit different parts of the plane. A photon hitting the nose comes back a tiny bit faster than a photon bouncing off the tail. This spread of return times creates a highly accurate 3D depth map. A tiny 280-pound decoy is going to have a super short timing span. A neural network can look at those random timings, realize the object is only a few feet long, and instantly label it a fake. Let's move on to the proof of principle. Now, it's one thing to sit around doing math on relativity and quantum mechanics. It's another thing entirely to build it in a lab and prove it works in the physical world. So researchers did exactly that. But before we look at their setup, you need to understand the magic ingredient, the BBO crystal. Think of this specialized crystal like a magical prism. You fire a standard blue laser into it, and it forces a single photon to split into a pair of entangled twins. They pop out with perfectly correlated timings. This crystal is the beating heart of the whole quantum radar system. Let's look at the actual experiment. Here's how it builds. A laser fires right through that BBO crystal. The signal photon goes straight to a detector to be time-tagged. Meanwhile, the idler photon gets shot out of a telescope toward a black aluminum target. They painted it black to mimic the deep absorption of modern stealth materials. The photon bounces off, changes polarization, and flies back into a second detector to check for that crucial coincidence match. And it absolutely works. Finally, let's talk about the current limits and where this is heading in the future. As mind-blowing as this is, we have to be totally honest about where the tech actually stands today. Scaling this from a lab bench to a battlefield-ready system that can spot a stealth bomber at 30,000 feet is a massive engineering headache. Just look at this graph. This perfectly illustrates the biggest hurdle. The coincidence rate, our ability to match those delicate twins, drops off a cliff over distance. Atmospheric interference and absorption just eat the photons up. The further out you look, the fewer pairs actually survive the round trip. Right now, the effective range is just under 1 kilometer. A huge part of that is because our current single-photon detectors, called avalanche photodiodes, just have a tiny bit too much lag. We call it timing jitter. It means we literally miss that incredibly tight fraction of a second coincidence window. To make this work at scale, we need much better detectors, massive telescope lenses to catch more returning light, and crazy supercomputer processing power to run those relativistic math corrections in real time. But here is the major takeaway. Every single limitation we just talked about, they are just engineering hurdles. There are no fundamental laws of physics saying this can't work, the math is rock solid, the quantum mechanics behave exactly as we predict. It's purely a matter of building faster, more sensitive components. And if history tells us anything, optical and electronic tech evolves incredibly fast. Which leaves us with a truly fascinating question. When quantum detector technology inevitably catches up over the next 5 to 10 years, will the trillion-dollar era of stealth aircraft and electronic decoys simply vanish overnight? We've spent decades and fortunes building invisible planes, but the quantum realm plays by a totally different set of rules. The unbreakable secret handshake of quantum radar might just render the ultimate camouflage completely obsolete.